Hello, here's your Lab 10A video on the goodness of fit tests. We're going to get into some cool things with our new chi-square distribution. But first, what is this test for? And let me hide my floating meeting controls. There we go. This test is for when we want to do not one, not two, but many means, three or more proportions, not means, proportions. And so to do this, we're going to use a modification of the normal distribution. So here's our standard z distribution, which is the normal 0, 1 distribution. Here's a plot of that. I'm using the curve function, which just takes a function, the density of the normal distribution, and plots it. So this is the curve that we used for finding probabilities with p-norm. And so the question is, what if we take this z distribution, and what do you think it'll look like if I square the inputs? So I get all these values. I get anything from 10 to negative 10, but whatever I get, I'm going to square it. You can guess that negative values are going to become positive. So all these values on this chart are going to get placed over here, but they're also going to get squared. So tell me in your own words what you think that's going to do when we square all these input values. So once you've done that, you can check your thinking. Here's what it looks like when I square that. Here's the actual density function for it. So the values that are close to 0, 0 is the most common value. That will occur the most frequently, and it's going to drop off. But yeah, so that's the z-squared distribution. It's got a little bit of a wider tail than before. It's got an interesting drop off. So this distribution we're going to use, but we're going to add many z distributions together. And when we do that, we get what's called a chi-square distribution. So if I take k different z-squareds, it could be any number, any integer, we would call that the chi-squared distribution with k degrees of freedom. Okay, so this is characterized. We'll look at this. Let's look at some plots, and you can see what it's characterized as. Here's the chi-square distribution with 1 degree of freedom. Notice it's exactly the same thing as the z distribution, the z-squared distribution. So one distribution looks like what we just did before. And now let's look at what happens when we add more and more of these guys. More and more z-squareds together. So 1 degree of freedom would be 1 z-squared. This would be 2 z-squareds added together. And so this kind of plots it all together, and you can see the yellow is the 1, red is 2, purple is 3, blue is 4. So it's got this shift. It's going to the right, and we got this right skew. For all these graphs, there's still more data to the right. The chi-square distribution is always going to have a little bit of right skew. And so let's start looking at, this is the distribution we're going to use for doing our test of many proportions. So let's start practicing how to find probabilities with it. Here's an example of our chi-square distribution with 10 degrees of freedom. What appears to be the most common value for this? We look at the graph, looks kind of like 9. The most common value, yeah, somewhere around 9. It's interesting. If you look at the mean will actually be 10. Notice there's skew to the right, more data is to the right, so that'll pull the mean to the right. So you could say something around 9 is the most common value. The mean is actually same as degrees of freedom, which is 10. That's just a characteristic of this graph. Kind of good trivia, good thing to know. All right, so now let's look at finding probabilities. Now that we're comfortable with our distribution, what if I want to find the lower tail probability of something that is, looks like we have 3 degrees of freedom is what I've put here. And I want to know the area of everything less than 6. So I've highlighted that area. Here's just a function that does that. I used echo equals false because this is code that I've made. I don't really think you're going to use it. I just don't expect you to. So when you knit this, this code will not show. That's what that means. Okay, so let's use p chi-squared to plot this distribution, to find the area of the lower tail. P chi-squared. The first value, you notice this little yellow box pops up and says Q. So Q is our quantile, that is our cutoff. So we'll say Q equals 6, and degrees of freedom is just what's specified to make our distribution. We got a lower tail probability of about 88%. So now let's find the lower tail probability of a chi-square distribution with 4 degrees of freedom with everything below 4.3. If you want to use this function to plot what that looks like, you could say we want to know everything. Oh yeah, we want to go 4 degrees of freedom, x0 and x2. These are the bounds that, sorry, x1 and x2 are the places that I'm highlighting. So I'm going to go everything from 0 up to 4.3 for the lower tail. So that's the area I'm trying to find. So let's find it. Using p chi-squared. The cutoff is 4.3. And the degrees of freedom is, did we say 4? Yeah, 4. There you go. Check your work. All right, and I'll let you do the last one on your own. You're finding one more lower tail probability. And pause it. Do it on your own. Don't look at my work. Only once you've done it should you check with my work. There you go. 5 degrees of freedom, lower tail of 5.1. Great. So now that we know lower tails, we can do upper tails. Suppose I want to do everything above 4.3 on that same 4 degree of freedom graph. Probably guessed it. We'll do the same thing as before. We'll say 1 minus to get the upper tail. 0.3 is my cutoff, and my degrees of freedom is 4. Notice I could put Q in here. Q is the name of the quantile, but you don't have to. It runs the same either way. Let's find the upper tail probability of the chi-square distribution with 5 degrees of freedom, starting at 5.5. I'm going to plot that for you. We got 5 degrees of freedom, and I want to go everything from 5.5 up to what the maximum is on my graph. I don't go above 20 on my graph, so that's the area we want. Find that upper tail probability. Please do this on your own and then check. 5 is my cutoff. Freedom was, no, actually looking at 5.1 here. That's my cutoff and 5. Let you check your work there, and you do the next one on your own. And then when you're ready, let's do some goodness of fit testing. So here's how we're going to actually look at the data. So here's a data set that I got of people that were selected for a jury. How many total were there? I'm kind of curious. I can say sum of jury, my table. Let's look at that. So I have 275 people on my jury. 26 are black, 25 Hispanic, 25 white, 19 were other. And it looks like the way the table makes these, it's just alphabetical. So that's just the order that it does it in. And I can make my table. Another cool way to get that sum is you can say add margins, and it puts that sum on the end. So that's my data. Now, the question is this jury representative of the actual population? So we also have data on what proportions the populations are. So if I run that, I see 7% were black, 4% Hispanic, 72 white, 9% other. So how many people would you expect for each race in the jury sample? So for black, if there was 275 people, 9% of them I would expect to be black. So I'd expect to get about 24. Let's do that for white now, or for Hispanic. 12%. So 12% of 275 will be how many expect to be Hispanic, and so on, so on. I'm going to be fancy. I can just say, if you see the pattern, I can say population times 275. and that'll give me my expected counts. So we're going to use those now. Okay. So what are we going to test? We're going to test the hypothesis that the probabilities of choosing people for the jury are the same as the probability or the distribution of that city or whatever. What does the information say? Is the same as the proportion of registered jurors. Same. So we would expect these counts to line up with the actual counts, right? That's our null hypothesis. Alternative says, no, at least one category has differing. Okay. So as I mentioned above, we can get this population times 275. That gives us what we call our expected counts. That's what we expect to get. If it were to be evenly distributed according to the population of the area, we'd get that. The observed counts, I'm going to call that OBS, is what we would get from the jury. So that's all our data. Now we're going to start crunching our numbers. We got our null hypothesis, the expected counts, the data itself is the observed counts. So we're going to find our p-value, which is the chance we've observed this data if the null is actually true. So what that statistic is, I take the observed minus expected for each group, square it, and divide the expected. So we're going to add them all up. So here we go. Here's again our data. Let's do this. Let's type this out. Chi-squared will say we take our observed, which is 26 for the black category, minus what we expected, square it, and divide what we expected. That's the formula. Observed minus expected over expected. And I'll keep doing that. 25 is what I observed, minus 33 is what I expected. Square it, divide by expected. Then for other category, I'll get 19 observed. I would expect 24. Square it, divided by that expected value. And then lastly, the whites, we observed 205. Looks like they're a little bit overrepresented. We'll see how much. I did. Okay, so this is, I believe I typed that incorrectly, but if I want to be careful and check it, I could say observe minus expected, square it, divided by expected. That would give me for each category this deviation. So then I said add it up. I add this up. This is just a quick way to do what I just did. And so indeed, I'm getting the same value. That's nice. So it's important as you understand where these values are coming from. We're taking expected deviations for each group, squaring it, and divide it by expected value. So this is called a chi-squared statistic. This value here is what we're going to throw onto our chi-squared distribution to see what it tells us. But we have this caveat that says, well, there's some conditions for using our chi-squared distribution. First is independence. All the data must be selected independently of each other. I would hope so for a jury, but may not be the case. And then we got the sample size. There's at least 5 expected counts. So let's check. Independence. Let's say we hope so. At least they weren't choosing people like based off any previous information from the previous selection. So we hope so. Let's see, sample size. Is each of our expected counts greater than 5? So we can look at those, and indeed they are. So 5. Okay, so those are the kind of things we have to check. We're using our distribution. Now we're going to find our p-value. P-value is the probability of observing something greater than what we observed on our chi-squared statistic. So that value we found above, we're going to say, what's the chance of observing something greater than that? And for your benefit, I'm going to make myself plot that. I'm gonna plot that p-value, give you the picture. Or this is scrolling. Okay, so I want to find the probability of observing more than this number here. That's my cutoff. And the question is, well, how many degrees of freedom am I messing around with? And the answer is, if it's a fixed number of people, we will fill only all but one of the categories until the rest is fixed. So that's a brief explanation. We're going to use k minus 1. So in this case, we have 4 categories. We're going to use one less, k minus 1. So 4 minus 1 is 3. That's the probability we're going to find. So now you know how to do that. And say our cutoff degrees of freedom is 3. So that's our p-value for this case. So what I will say, p-value, not so small, but it is somewhat small. I'm going to say we have marginal evidence. We have marginal evidence to reject the null, which says there's no deviations between the expected and the observed. So we have our marginal evidence of bias, but it's not strong. This example will tell us. So for your benefit, I've given 2 practice problems. You might have questions on how to set these up. If so, please come to class. And maybe for one of these, let's see, for the textbook one, I'll set it up with you. Okay, I'll help you set this one up, but I'll leave the remaining one for your own practice. So what I'm going to put in here, take a second to read this problem. But what we have is professor, he's getting these textbooks. He expects that 60% of students will purchase hard copy, 25 web, 15 online. So this is what he expects. I'm going to call this the expected proportion. And it looks like from this, he has 126 total students. So if I multiply this by 126, you'll see we get expected counts. That's important. When we're finding your chi-square distribution, you're using the counts, not just the probabilities. That's why I'm multiplying by the 126. Show me that, well, 60% of that is 75.6 students, 25 is 31.5, so on. Those are my expected counts. Here's my observed counts. This is what we actually saw in the class, 30 and 25. So the question we're going to ask in this problem is there a statistically significant difference between these 2 sets of counts? So you can practice setting up a hypothesis. We did that above. You can see an example of that previously. How many do you expect? Well, I actually just did that with you. Conditions, and then finding your p-value off your statistic. And then lastly, of course, interpreting your results in context. All right, there you go. I'll give you a start. Good luck with your practice, and we'll see you in class. Have a good one.